What's up, guys? We just saw a first order reaction in a batch reactor. If you haven't seen it, just go previous and you will see that video. I recommend it before starting this one. But in theory, you could go and jump directly to a second order elementary reaction in a batch. We are analyzing isothermal reactors, and because it's only one reaction, we are going to use conversion. So, given this rate of reaction here, look at this to the second power, calculate the time needed to achieve certain conversion. Essentially not only certain conversion, but 90%. So, let's do it. The only thing that changes is the actual rate of reaction here. We have it to the second power, because this is our design equation. It applies for every batch. Given, of course, it's isothermal and has no inlet, no outlet, and it's constant volume. Okay, so from here, we're just going to, you see this value here and this value here, they are the same. So we can just plug this value here, plug it here, and you will see we get rid of the negative sign, of course, because this is minus RA and this is minus RA. We cannot send this negative, or if we send it, we will have to multiply minus times minus, which doesn't make sense. So just plug it here. Now you probably are checking that this negative sign will go here. And not only that, because if you've seen the previous video, you know that we're going to change this one here, and we get this equation. The relative concentration, of course you need to have concentrations here, and time, because we have no things depending on time. Actually, this constant is not time dependent. We could have it here, wherever you want. We will solve this first order differential equation. So first things first, initial concentration to final concentration, initial time, which normally is 0, but it could be any value. Actually, you can start counting in 5 seconds, and the final time. So solving this, hopefully you know a little bit of integrals. If not, just check out or simply just trust me. Hopefully I'm right, because I got this value here, which is very important to get the negative sign here, and yeah, these values here, we just need to plug them in here. This, because this is constant, it goes out, and you know that the integral of 0 to t, derivative of t, will be time. Now let's solve this. Let's plug in the concentration of A, and you know that this is actually, let's say this is minus, and you got this value. Just because I want to make sure that you guys don't get confused. So this first goes negative, because it's negative times positive, you get negative value, and negative times negative, you get a positive value. So essentially, you know that it's a difference, so they must be different. And the negative sign. If you have a mistake here, you will get to know, because normally you will get a negative value and you cannot have negative times. Or you can have them, but they are, let's say the data was given wrong. So once again, we want this in conversion terms. So how do we do that? We need to plug in this equation. So that's what I did here. Before I got this Ca, but I know Ca is equal my initial concentration times 1 minus x. So I got that here. This stays the same and the same. I could actually use this as common factor and take it out, and I will leave 1 minus 1 divided by 1 minus x. And if this is just math, guys, so this is 1 and 1. Look how this goes times 1, and this stays the same. And I'm also changing the k value to here, because I want time alone. Eventually I got this equation. Times equals the conversion divided by the constant times the initial concentration times the difference in conversion. So probably you've seen that in this time we do have a initial concentration dependence, because before we didn't have that. So right now we do have it. Why? Because it's a second order reaction, and that's very important. Actually, that's what I'm telling you here in the written statement. You do have a concept of initial concentration. And also note the K values. They might be the same numerical values but different units, because they need to make sense, of course. If you take away gramoles with gramoles, liters with liters, you get divided seconds, which division and division makes you multiplying, so that's why it's here over. Anyways, let's get the time. We got this conversion, and we actually need now the initial concentration, so they give it to you, 10 gramoles per liter, and you got this K value, which is the same. The only thing that changes is, of course, this value here, and probably because we are technically not cheating, but it is very strange that you will get the same constant if it's a second order equation. So comparing this one with the one of this here will be like comparing apples and pears or pineapples. They don't make sense because this is one reaction and this is other reaction. You can do it, but doesn't make sense. So substituting this data here, X goes here and here, concentration here, and you got this 9,000 seconds, which if you divide by 3,600, will give you the time in hours, which is 2.5. And we're done with this second order example. We're going to do a small conclusion in the next video. So if you do not understand everything, just check it again and follow through the next. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.